Hello, everybody. 2:05, time to start. So we stopped last time, which was yesterday, was here. So the last bit of chapter 5, which is the Vitali's convergence theorem. Okay, so we've made a simple lemma on the way to prove this, but we have to start by proving this result. And that will wrap up the sort of technical bits about uniform integrability that we needed. So what does this say? It says that remember, it says that if I have a sequence in L1 converging in probability to a limiting random variable, then convergence is in L1 if and only if the sequence is uniformly integrable. And I have also this third condition, which we sort of saw already in Scheffer's lemma, which is also equivalent. Okay, so let's prove this quickly. So I need to prove that I have convergence in L1, that X is in L1, and that the convergence holds. So first of all, for X to be in L1, how do I do this? Well, if I have convergence in probability, I know there exists a subsequence such that X and K converges to X almost surely. Okay, so I can write expectation of X. This is less or equal than lim_inf expectation of X and K. This is by Fatou lemma. Okay, this is the lim_inf of X and K, of course, is X. And this is now less or equal than sup over all n's of expectation of X n, which I know is finite because uniform integrability means in particular that the sequence is bounded in L1. Okay, so that gives me that X is in L1. So now I need to prove convergence. So what does it mean? It means that I need to look at expectation of Xn minus X, and I need to show that this goes to 0. Okay, so I'm going to take some epsilon. I'm hopefully going to bound this by epsilon, maybe 2 epsilon, let's see. So I'm going to split this again on the event that this is large and on the event that this is small. Okay, so an will be the event that Xn minus X is, let's say, larger than epsilon. Okay. I know that the probability of this goes to 0. So here I'm going to do something very crude. I'm just going to say this is less than Xn on this event plus expectation of X on this event. And here, of course, I'm just going to say that this is less than epsilon times probability of this. Well, I'm just going to say, let this to be epsilon. Okay. Fine, so I have epsilon here, and now I have these two quantities. But what do I know? I know that this family is uniform integrable, so I can replace this by sup over m's expectation of xm indicator of an. Okay. And then I have this, and then I have this one here as well. So this will be less or equal than, let's say, 3 epsilon, if I can show that these sets are small. So now n is fixed, and I'm thinking about all the x's. Okay, so what do I know? Uniform integrability means that for any epsilon there exists a delta such that if a set is small, so probability of set is less than delta, then this sup premium is bounded by epsilon. And of course I can add one more. The single random variable is also uniformly integrable. So I just need to have a control over an's. But what is probability of an? This is less than expectation of that sorry, no, this is not what I'm doing. I'm looking at that. That's right. So I'm going to bound this with the supremum of the what do I know about this? I know that this goes to 0. Sorry, I already know this because I have convergence in probability. It's even simpler. Right, so I know that this converges to 0 by probability. So for any delta, I can find n large enough so that this will be less than delta. And then I know that this will be less epsilon, this will be less than epsilon, and This is epsilon, so I get 3 epsilon. Okay. So that shows me that I have convergence in L1. So now from 2 to 3, this should be simple. So I'll just have to sandwich things. Let me get this right. So I'll have minus xn minus x less than xn. Let me write it x minus xn. Okay. So now I assume convergence in L1, which means that expectation of this goes to 0. So in particular, expectation of this goes to 0, which is exactly what I want. So now I need 3 implies uniform integrability. So of course, I'm just going to work with the absolute values of xn. So let's just define yn to be expected condition absolute value of xn. This will just declutter a little bit. So what do I want? I will take random variables yn min k for some fixed k, and this will be bounded. And then I'll use the small lemma we proved yesterday, and then hopefully I can work with across the case. Okay. But before I do this, so then and I'll look at n yn min k. Okay. So if you look at this, okay, probability that this difference absolute value, so we get that absolute value of y minus yn is less or equal than, so that's this, is less or equal than absolute value of xn minus x. And this means that yn goes to y in probability, because probability that they're more than epsilon apart is less than probability that these are epsilon apart, which goes to 0. Okay, and likewise, I'm going to repeat this. Yn min k will converge to y min k in probability. Okay. Same argument. You can just observe that the absolute value of yn minus min k minus y min k is actually less than yn minus y. Okay, so I have these random variables and these ones, and they converge in probability to their limits. But if I look at these ones, they are now non-negative and of course bounded. So by lemma, so this is lemma 523 in the lecture notes, but this is the last lemma we shown yesterday. This means that the convergence in probability, and bounded means here that we have yn min k converges to y min k in L1. So in particular, I have that expectation of yn min k converges to expectation of y min k. Now what did I assume? Lest I forget, I assumed that expectation of yn converges to expectation of y. That's because that's how I defined yn. Okay. So now I'm going to look at expectation of yn min k. This is equal to expectation of yn minus, so what am I subtracting? I just have to truncate the bit where yn is less than k, so minus expectation of yn min k. Yep, if yn is greater than k, then so this is just equality on level of functions, and then I took expectations. Okay, so now this converges by this and by the assumption to expectation of y minus expectation of y min k, which then again is equal to expectation of y min k plus. Fantastic. So what does it mean? It means that for n large enough, these objects are all close to this object. Okay. And what do I want to show? I want to show that xn's are uniformly integrable. And to show that xn's are uniformly integrable, I need to show that I have uniform control of this. So I need to show that limit as k goes to infinity, sup over n's, expectation of yn minus k plus is equal to 0. But this now follows, right? Because what do I do? First I take some epsilon, okay? Then I take n0 such that for all n's greater or equal than n0, this quantity minus that quantity is less or equal than, I don't know, epsilon, if you want. Now this, so first let me maybe fix k. So I need, this is for each k, so let's take epsilon, then let's take k large, so that expectation of y minus k plus is less than epsilon, if you want. Okay. I can do this because y on its own is of course uniformly integrable, so I know this goes to 0 as k goes to infinity, so I can pick that. And so this tells me that for n large, all of these quantities are now less than epsilon plus epsilon, so 2 epsilon. This leaves me with finitely many n's to check, so all n's from 0 to n0. But of course, that's a finite family of random variables in L1, so that's also uniformly integrable. So again, I can pick k large enough so that they're all less than epsilon. Okay. So this controls these variables from n equals 0 to n0, and then the limiting one takes care of the rest. Any questions? Happy with this? So the other bit which I made remark about, this is actually stated as theorem 611 in the notes, is the following. So if you have x in L1 and f alpha, a family of sub-sigma algebras in my F, then x alpha defined as conditional expectation of x given f alpha, this family of random variables is uniformly integrable. Proof. So first I'm going to look at absolute value of x alpha. Okay, so this by definition is the absolute value of expectation of x given f alpha. And now conditional Jensen tells you that this is less or equal than expectation of absolute value of x given f alpha. And now if you take expectation on both sides, you get that expectation of x alpha is less or equal than expectation of x in absolute value, and this is finite. So in particular, this family is an L1 and is bounded. The norm is bounded by the norm of x. So now we need to compute. So there we're looking with the positive, the sort of hockey stick functions. Let's go back to definition of conditional of uniform integrability here. So I'm going to look at expectation of x alpha indicator x alpha is greater than k. So this is now less or equal. This random variable is less or equal than this random variable. So by monotonicity of expectation will tell me this is less or equal than expectation of conditional expectation of x given f alpha indicator x alpha greater than k. But now this indicator is itself f alpha measurable. This whole thing goes, of course, for all alphas in my index set. This is measurable, so I can pop it in, and I have expectation of conditional expectation. So this is equal to expectation of x indicator x alpha greater than k. What's my aim? I want to show that this is uniformly small across alpha for k large enough. Okay. So I just need to show that I have control over this. But the variable x on itself, of course, is uniformly integrable. So if I can show that for any delta, for k large enough, this is smaller than delta, then I will know that this is less than epsilon, right? So this is, so for any epsilon, so if I fix epsilon, then by uniform integrability of the random variable x on its own, this will be less or equal than epsilon if the probability of this event is smaller than some delta from the property of my from the alternative characterization of uniform integrability. But I can compute this, of course, but Markov will tell you that this probability is less or equal than expectation of x alpha divided by k, which is less than expectation of absolute value of x divided by k, and this is less than delta, taking care k greater than, well, expectation of x divided by delta, right? So first, if I had epsilon, I had delta from this, and I took k large enough, and so I see that for k large enough, this is uniformly controlled across lambda. Okay, is this clear? So I'm constantly playing around with the sort of the definition of uniform integrability and its alternative characterization, right? Because here it's quite convenient to have one variable here and different sets here. Well, here I have the same, of course, the particular set. Good. So let's go back to martingales. Okay, we've done a bit of additional homework to get the extra tools. So last time we saw that a martingale remains martingale across stopping time, so that we can really, right? We saw that if m so a martingale m satisfies m tau is equal to the conditional expectation of m rho given f tau for rho tau to bounded stopping times. And so our next step is to extend this to arbitrary stopping times. And indeed, this sort of next step will be also to extend this to stopping times which can take value infinity. And then to understand, when is it that I can talk about m infinity, where I can actually do things. And while we have this result here, maybe it's worth to make this remark that somehow, if there exists an m infinity such that mn from 0 to infinity included is a martingale. So if I can make sense of this object, then what should happen? It should happen that mn is equal to conditional expectation of m infinity given fn. So in fact, you see that if you can sort of close your martingale in this way, then the whole martingale is defined just from one random variable and the flow of information that you have. And of course, you see straight away from what we just shown that this family of variables is uniformly integrable. So if it ever happens, your martingale has to be uniformly integrable. And we'll see that this is actually equivalent. So the martingale is uniformly integrable if and only if you can close it with a random variable m infinity such that this holds. But we'll probably get there. We'll actually get there next week. So let's start with a stopping theorem. So I had Doob's optional sampling theorem. I'll now have a theorem which I'll call, just to have a little bit of confusion, I'll call it Doob's stopping theorem, or a variant thereof. Okay. And so what do I have? I have m, a martingale, and tau, an almost surely finite stopping time. Then I claim that expectation of m tau is equal to expectation of m0. So I would like this to be always well defined. Tau is an almost surely finite stopping time. So on some null set, it could take value infinity. So I'm just going to kill this random variable where it's not defined, because mn is defined for all integers. So I'm just going to put tau infinity, less than infinity. This is an indicator of a set of full measure. So it doesn't actually change this expectation, but it makes it well defined, because otherwise I couldn't really define m as a variable, as a function on omega if tau is equal to infinity. This was on a null set, so I don't really care. Okay, so that's why I have this indicator here. If either, so I'll have two conditions which guarantee that this holds. The first condition would be that m is uniformly integrable. So the family of variables mn is uniformly integrable. And the second one will be something about the conditional increments. So I'll say that expectation of tau is finite. So that somehow tells you that the stopping time itself is not too big. And there exists a constant such that the conditional expectation of the increments, the absolute value of the increment, is less than L, almost surely, for any n greater or equal than 0. So let's prove this. So the first case, what do I have? I assume uniform integrability, and I want to obtain this, this expectation, the equality between expectations. So I'm of course going to use the Vitali's convergence result. There, right? I want to have uniform integrability, and I'll use our previous result, and then I'll take limits. So let's try to do this. So what do we know? We know that mn minus k plus is a sub-martingale. So we know that if M is a martingale, then the absolute value of M is a sub-martingale. And then I then apply a non-negative convex function to a sub-martingale, so I still get a sub-martingale by, again, by conditional Jensen. So essentially I'm using conditional Jensen inequality twice, but you can also just use it once explicitly on that function, which x maps to absolute value of x minus k positive part. So that tells me by the previous theorem we've just shown for bounded stopping times, so essentially taking expectation there, okay, we had this for martingales, but we also saw that for sub-martingales, I preserve sub-martingale property. So what does it mean? It means that in particular expectation of mn min tau minus k plus is less or equal than expectation of mn minus k plus. Great, because what does it mean that that m is uniformly integrable? It means that I can control this uniformly in n, right? So that the sup over n's of this quantity in k going to infinity is 0, and in particular that also means that the same holds for the left-hand side. Question?
When you've written m n min tau, is that just a regular m or the m for like the family of the martingale?
No, so that's the regular m. So I need to, right? So for this to make sense, it has to be a random variable. Yeah. So my bold m, right? So my bold m, which I always try to write like this, it denotes the whole. It's just the notation for the whole sequence. Okay.
Oh, it's absolute value.
This is absolute value. Sorry, that's absolute value. Yes, I can see you. This looked a bit like my bold m. That's absolute value of m. Okay. So this is a submartingale. So I know that if you call this yn, okay, then being a submartingale in particular, the optional sampling theorem tells me that expectation of, well, if I want to use that, it will even tell me that y n min tau is less or equal than the conditional expectation of yn given fn min tau. Then I can take expectation here, and I'll have that expectation of this is less or equal than expectation of yn, which is exactly what I wrote here. Okay, so this is, I'm using that theorem, the Doob sampling theorem we had for bounded stopping times, with the bounded stopping time rho is n and tau is n min tau. Okay, so this tells me that the family mn min tau is uniformly integrable. I have that mn min tau converges to m tau, indicator tau is less than infinity, almost surely. This is clear statement. This sequence from some point onwards, because tau is finite, is equal to tau. Okay. And so it also converges in probability, and now because of uniform integrability and Vitali's theorem, I get that mn min tau converges to m tau also in L1, and hence in particular expectation of absolute value of m n min tau, or I don't need absolute value, I want this actually, converges to expectation of m tau, indicator tau is finite. But this, of course, is equal to expectation of m0 by, again, the sampling theorem, because n min tau is a bounded stopping time. Okay. So this is, in fact, a constant sequence which converges to this, and hence limit is equal to this. And I'm done. Here, so this is somehow, somewhat sharp, you can see, because of the equivalence there. Here, I'm giving you a sufficient condition, and I'll just use, let's just use dominating convergence theorem. Okay. So without loss of generality, I can always assume m0 is 0 because I can subtract the initial value from my martingale. Okay. So I can write mn min tau, which is then mn min tau minus m0 because that's 0. And I can write this as telescoping sum, and then this will be less or equal than sum of conditional expectations. So I'll have sum of m k min tau minus m k minus 1 min tau. And this is for k equal 1 to n. So I can rewrite this as mk minus 1 indicator. So how long do I keep counting these? Well, all the way until k is equal to tau. So I need tau to be greater or equal than k. At the moment tau becomes less than k, I stop counting. And so this is less or equal. Now what I'm going to do, I'm just changed n to infinity. So k equals 1 to infinity. And this is my psi, a random variable. So now this is a random variable, which is of course non-negative, and it dominates this whole family. Okay. So I have m and tau converging to m tau, indicator tau finite almost surely. This still holds. And now I have a candidate psi. If I can show that psi is integrable, then so if psi is in L1, then dct tells me that expectation of this converges to expectation of m tau as I wanted. Okay. So all I have to show is I have to show that psi is integrable. So let's try to do this. Expectation of psi. This is equal by monotone convergence theorem. This will be equal to sum of expectations of this increment. So mk minus 1, indicator tau greater or equal than k. 1 to infinity. Tau greater or equal than k. What is this said? Tau greater or equal than k. This is the same as tau less or equal than k minus 1 complement. Okay. So this is in f k minus 1 by definition of stopping time. So I can condition here on f k minus 1. And now so I'll have this bit here and then times this bit here, and this bit will pop out because it's fk minus 1 measurable. And so what am I going, and I'm left with something on which I made an assumption, right? So all in all, I have expectation of expectation, so sum, expectation, indicator tau greater or equal than k, and here I have conditional expectation of the increment conditionally on fk minus 1. And this is less than L. This was my assumption. Okay. I've made the assumption on the conditional increments because this is the way it's often easiest to verify this. Of course, you can take expectation here on both sides, and this tells you also this bound carries over to the expectation. Okay, so this is now less or equal than L times sum of probabilities that tau is greater or equal than k, and this is less or equal than L times expectation of tau, which is finite, and we're done. there's an example 820 in the notes of application of this theorem. I think if you look at the last a couple of last papers, this type of example often makes it to the exam in one way, form or another. It's a very, very typical way to apply. So you have some sort of statement. In this case, we're seeing digits drawn IID from some distribution over integers, and we're asking what is the expected time until a certain pattern appears. Okay, 2, 3, 5, 7, 1, 1, 1, 6, 8. Okay, and there is a cute way to answer this problem by constructing a martingale and a sequence of stopping times. You can interpret this as sort of casino where people enter and gamble on seeing this pattern in a fair way. I think it's useful to read this example sort of carefully. Some will see this straight away. Sometimes it's easier, it's nice to take a bit more time to read this and make sure that you can sort of write this properly. But it's a useful example to analyze. And there are similar things that will appear now on problem sheet 4 as well. But this type of stopping theorems are really the sort of powerhouse of when we want to compute something in probability that happens in dynamic setup. Typically, the way you want to do this is you want to find a martingale such that the quantity you're interested in will fall from that statement. Okay, and then it's about finding the right description of the problem so that and isolating the martingale to which you can then apply the stopping theorem. So there's a couple of examples like this on the problem sheet and in notes for you to play around with. So I want to talk a little bit, actually the remaining time today, about Doob's and various maximal inequalities. So our aim is really to understand asymptotic behavior of martingales and when can we say that martingales converge and in what sense they converge. And useful thing on the way is to get some inequalities that control the path of a martingale using quantities for particular instance in time. So let me make this precise. I'll have two statements. So first one is Doob's. So again, you see Doob's name comes time and again. He really was the sort of person. He was based in Urbana-Champaign in Illinois in US mid last century and did a lot of sort of research and basic theory for martingales. So Doob's maximal inequality. So let X be let me take a sub-martingale. Then for positive lambda, I claim that the process yn lambda, which is xn minus lambda indicator, that max k less than n x k is greater or equal than lambda, that this process is a submartingale. And in particular, I know that expectation of xn, of yn, okay, is greater or equal than expectation of y0, and this will tell you that lambda times probability that the maximum of xk is greater or equal than lambda is less or equal than expectation of xn. So I'm being a bit more specific here than this is often done, but so you can forget about this middle bit if you want. And the statement that you would most often see would tell you that probability that the maximum of your process goes above certain level is, so this is something about the path between time 0 and n. And on the right-hand side, this is controlled by expectation of xn in absolute value divided by lambda if you want. Okay. So let's prove this. So I'll take tau, which is the first hitting time of lambda to plus infinity. So this is the first time that xn goes above the process, the level lambda. And I'll set Vn indicator tau is less or equal than n minus 1. So this is the same as saying that at time n minus 1, lambda has been breached, right? So it just says that max of xk, k less than n minus 1, is greater or equal than lambda. This is, of course, fn minus 1 measurable, because that tau is a stopping time, because it's a hitting time. Right, so I'm now becoming a bit quicker and quicker, but I think it's, you should really note that it's a nice edifice we're building, so we're using a lot of small previous results we've had on the way. So we've discussed the fact that the first hitting time of a Borel set by an adapted process is a stopping time. X is a submartingale, it's adapted, so this is a stopping time, etc., etc. Okay, so all of these things really come together. And now also, this being fn minus 1 measurable and non-negative, this is a predictable process I can use in discrete stochastic integral to construct more submartingales from a given submartingale. So I'm going to look at Vxn. So this is, remember, sum of Vk xk minus 1. Okay, this is a submartingale. But what is this process? Well, I'm summing. Tau has to be less or equal than n minus 1. Okay. So in fact, the first time this turns on is at time where n is such that tau is equal to n minus 1. Okay. So in fact, if you work this out, you will get x n max tau minus x tau. Okay, so in this telescoping sum, this will be 0 until the first instance where this holds with k, which means that this becomes x tau, and then I keep adding until I get to n. And of course, if I've never got to n, so if tau was larger than n, then this is x tau minus x tau, so it's 0. Okay, so you can also write this as xn minus x tau, indicator tau less or equal than n. So this is very close to what I wanted. See, then I can right? These sets are the same. So it's almost what I wanted, except there I had lambda, and here I have x tau. What's the relation? Well, from this you see that x tau is greater or equal than lambda. It's the first time you go over lambda. You could hit lambda, but you could, of course, overshoot lambda. So in fact, there I'm subtracting something smaller. So the difference between these two processes, what do I need to add to this process? I need to add to this process x tau minus lambda. Okay. Indicator max xk is greater than lambda. So this is a funny process because you see it starts most likely in 0, and then it makes one jump, and this jump is equal exactly to the difference between x tau and lambda, and then it stays constant. Okay, so it's an increasing process. And hence it's also a submartingale. And hence the sum of this process and that process, so the n is here in this process, right? The sum of these two is also a submartingale, and this is yn lambda. Fantastic. So now I get that expectation of y lambda 0 is equal to expectation of y lambda n, sorry, less or equal. That's just a consequence of submartingale property. This is equal to expectation of xn minus lambda, indicator of the set I'm interested in. What's y0? Well, this is expectation of x0 minus lambda, indicator x0 is greater or equal than lambda. So this is in particular non-negative. Okay, so now we know that this expectation is non-negative, and this expectation being non-negative is precisely this inequality here. And that inequality is trivial. I've replaced xn by its absolute value, and then I've dropped the indicator function. Maybe let's have a corollary. So if I have a martingale and assume that Mn is in LP, so I fix some p greater or equal than 1, then I can look at probability that max of mk and this will be less or equal than expectation of mn p lambda p. And what did I do? I'm just applying that result to the process. This doesn't change anything. Absolute value of mn to power p, and of course this probability is the same as if I put p here and p here, and then I just have that inequality there. Maybe a bit more interesting is the following result. So this is known as Doob's LP inequality. So I'm going to take p strictly greater than 1, and I'm going to take x a non-negative submartingale. So you should think of absolute value of martingale as your canonical example of a non-negative submartingale. Okay? Just stating this in a slightly more general context. Such that xn belongs to LP for all n greater than 1, then max of xk, so I can maybe denote this x bar, also belongs to LP. And in fact, I have an explicit bound on the pth norm of this maximum. So the pth norm of x bar, and I want to do this with p, let's have it like that, is less or equal than, let me call it this, p over p minus 1, the pth norm of xn. So I'm not sure if... Has anybody recognized this condition from here to here? Okay, especially if x is non-negative, right? Then you can drop this absolute value. And we had this condition on problem sheet 2. And there was a problem which is also a lemma in the lecture notes saying that show that if this holds, then a certain relation between the LP norms holds. And that's exactly what I wrote here. Okay. So this result tells you that the pth norm of your maximum is controlled. So of course, this inequality is trivial because that random variable is always greater or equal to this random variable. It's this one which is interesting. Okay. So it tells you that you can control the whole path. So this is maximum over the whole path through this. Okay. And the way you want to think about applying this, okay, if you get a martingale in LP, so a martingale such that Mn is integrable with pth moment, that tells you that maximum of absolute value of mk, k less or equal than n, is in LP. And obviously this random variable is something that you can use in DCT to dominate the whole path. So whatever you have for the that concerns your random variables, then you'll have this. And so in particular, from this results, you see you can deduce quite a lot. If you have results for bounded stopping times, you can take limits if you have such control. In particular, if your process M is X here is bounded in LP, so that this is less or equal than some constant which doesn't depend on n, then you can take n going to infinity here, and you'll know that this maximum over the whole path is suddenly integrable in LP, and you really have, you can play around with DCT as much as you want. And we'll see this later on in problems. So this is quite a powerful result because it really tells you something that allows you to control the whole path of your martingale using just the final value, well, sub-martingale. So in particular, absolute value of my martingale. You can derive many other maximal inequalities. There's one more in the notes for a super martingale that you can play around with. If you want, we won't need this. It might get used in the continuous martingales course. And what we're going to do next week, okay, so we have 2 more lectures, and next week we really start studying the convergence of martingales. So we'll see that using these results and in using stopping theorem, we can control how many up crossings and down crossings of an interval our martingale makes, and that will allow us to prove when martingales converge, almost surely, and then also using our notion of uniform integrability when they converge in L1. Okay? And then finally, we'll use this to prove the strong law of large numbers, which will probably be the last 20 minutes of the last lecture, and we'll finish this course. All right, I'll see you next week. Thank you.